Last time we talked about electric arcs and they were electrically augmented flames. I said that 99% of the current is carried by the electrons, and I started to talk about high pressure arcs, and I'm saying the unconstricted high pressure arc, a plasma arc, which is essentially where you strike the arc inside a constant volume chamber, that's a constricted arc. But an unconstricted arc is one that just operates at 1 atmosphere of pressure. It turns out that an unconstricted high pressure arc, 1 atmosphere of pressure, is only partially ionized. If you look at the Saha equation, which is, this is the solution to the Saha equation, and you look at the mobility of the electrons, and you want to carry 100 amps across a 1 centimeter gap that has about a 1 square centimeter cross section approximately, and you calculate how many electrons you need to have in order to carry the current, 100 amps of current, you will find that you only need to be at a temperature of around 10 or 12,000 degrees Kelvin. And in fact, if we measure the temperature of an arc on a piece of water-cooled copper base plate, we will get 10 or 11,000 degrees, 10, 11, 12,000 degrees, depending on the shielding gas. If in argon, it'll be around 11 or 12,000 degrees. At that temperature, the ratio of argon atoms to argon, or argon atoms to argon ions is probably only about 5%. If you go up a little bit more in temperature, if you're at 1,000 amps, well, maybe it's 30% ionized. But these are pretty steep curves, and so you don't go up much in temperature to get a lot more ionization and get a lot more current flow. What happens is, in an unconstrained arc, if you try to put more current through it, the arc gets a little bit bigger, but it also gets a lot hotter, and so it carries a lot more current because of the steepness of these lines with temperature. Why is this interesting? Well, it's interesting because that's why physicists will not study welding arcs. They say it's because, oh, that's mundane. No, what they really mean is it's too difficult. Physicists like to study two types of plasmas: fully ionized plasmas or weakly ionized plasmas. In a fully ionized plasma, every particle there is ionized, or 99.9% of them are, and therefore they can treat every particle as either positive or negative charge, and they don't have to worry about neutrals. If I have a weakly ionized plasma, I'm 1% ionized or less, and every surrounding particle is basically a neutral atom around a charged particle. And the physicists can mathematically handle that. If you get into 5 to 30% ionized, you have a statistical problem here that you can't write down simple mathematical equations to handle. And so physicists don't study mundane things like 1 atmosphere or high pressure arcs because they're difficult. They don't tell you that's the reason, but that's actually the reason. They're too hard for them to calculate. You have to remember what Theodore von Karman said: a scientist explains that which exists, an engineer creates that which never was. And I told you the corollary to that, right? The Media Lab creates that which never will be. Anyway, if we, so the whole thing will ionize enough to carry the current, and it will not get to a higher temperature. Let me back up for just a second and point out that this 10 or 12,000 degrees is basically for an argon arc. If I were to run a helium arc, and argon has an ionization potential of 14.6 volts for the first ionization energy. Helium has one of 24.5 volts, almost 10 volts higher, and that will shift. You'll have the exact same type of curve, but it will just shift it to higher temperatures. So a helium arc, this point where you get 5 to 30% ionized, is not going to be 12,000 degrees, it might be 18,000 degrees. So if I have a piece of water-cooled copper and I strike a pure argon arc, I'll get 12,000 degrees as kind of an average arc temperature. If I strike a pure helium arc, I'll get 18,000 degrees. And people for years have said, well, that's the reason that helium produces a hotter arc and more efficient melting in welding. No, sorry, not right. And we'll go through that in a little bit, but basically what happens, I'm not welding with an argon arc. I'm not welding with a CO2 arc. I'm welding with a metal vapor arc. It turns out when I liquefy the pool, I'm getting sufficient energy to get 5 or 10% metal vapor up in that plasma. And in fact, that 5 or 10% metal vapor doesn't have a 14.6 volt ionization potential. It has a 5 or 6 volt ionization potential. So it drops all these temperatures down to the 5,000 or 6,000 degree range if I had a pure metal vapor arc. Now I don't have a pure metal vapor arc. I have a partially argon up near the top of the electrode. In a gas tungsten arc, it's nearly pure argon. And down near the well pool surface, it's almost all metal vapor. So I have a mixture. And so the actual temperatures of welding arcs as measured are around 10,000 degrees, not 14,000, or not 12,000 or 14,000. They're around 10,000 because it's some sort of mixture, an average between a pure metal arc, metal vapor arc of 5,000 degrees and a pure argon arc, which might be 14 or 15,000 or 12,000 or whatever the number is, depending on the current you're carrying. So there is a different reason why helium does more efficient melting than argon, and we'll get to that in a little bit. Now, if we want to look at heat flow to the surface in a high pressure arc, you have a paper that some of this comes out. I've modified the numbers a little bit. It's a paper by Metcalf and Quigley, and they pointed out that the heat to the surface, Q, the total heat is equal to the heat from electron flow, convective heat from the hot gas, conductive heat through the hot gas, plus radiation heat from the gas to the workpiece. There also, you can subtract off the radiation from the workpiece out, which they do in their paper, and you can subtract off evaporative heat and other things. But the interesting thing here is it turns out that 80 to 90% of the total heat in the arc comes from the electron flow. It turns out that about only the arc itself is only about 50–60% efficient. A lot of the heat is just going off as hot gases in the atmosphere. But about 50 to 60% of the heat actually gets into the workpiece from an electric arc. And the electron flow creates heat by the following mechanism. It's the current in the arc times the work function voltage, the anode voltage drop, and the Thomson voltage. Well, let's talk about what those are. If I've got an electron sitting stationary in a vacuum, we call that, in physics, the zero energy level of the electron. If it's sitting at absolute zero, stationary, in a vacuum, not interacting with anything else, it's at a zero energy state. That's just the defined energy, zero state energy, thermodynamic definition. If I take that electron and I heat it up to some higher temperature, it has some thermal energy, right? If I'm above absolute zero. Well, that thermal energy is just equal to the Thomson energy. And somewhere, where did I put it? I have the thermal energy of electrons is basically given by the energy in electron volts, because I'm talking about electrons, is equal to Boltzmann's constant times the temperature. This is Boltzmann's constant times temperature is thermal energy. It has units of ergs or joules or whatever units you want. One unit is actually the electron volt, okay, is a type of energy unit. Very useful when we're talking about single atoms. If you remember, we talked about the bonding atoms of energies on the energy of bonding of atoms. And the primary covalent bonds and ionic bonds typically have 1 to 3 electron volts per atom. Well, that's the electron volts of energy. If I just rearrange this, the voltage is equal to kT over E, where E is the Coulomb charge. If we're talking about 300 degrees Kelvin, anybody in here an electrical engineer? No electrical engineer, no one's going to admit it. Anyway, electrical engineers tend to know that 300 Kelvin room temperature is, if you go through and put Boltzmann's constant in the Coulomb charge in here, and you're working in Kelvin, the voltage here works out to be about 25 millivolts. And the reason they need to know that is if you're dealing with semiconductors and you want to know how much thermal energy an electron has, that's going to tell you how much noise, thermal noise is in your circuit. It turns out it's about 25 millivolts. Okay? At room temperature, the thermal noise of an electron is 25 millivolts. And it all comes from just this simple little equation, which is just the temperature divided or multiplied by Boltzmann's constant divided by the Coulomb charge. Okay, and the temperature of the arc we know is around 12,000 Kelvin. If I take this, I go through this, the Thomson voltage in an arc is on the order of 1 volt. The electrons are not at zero energy, they have plus 1 volt of energy because they're very hot, or they will become very hot in the plasma. Okay, so we know that the heat from the electrons, due to the fact that they're not at absolute zero temperature, but they're hot in the plasma, if an electron's in the middle of a plasma stationary, just because it's hot, it will have about 1 volt of thermal energy. Now, it's not going to give up all of that 1 volt. It's going to go into a well pool that might be at 2,000 degrees rather than 10,000 degrees, so it may only give up 0.8 of its volt, of its Thomson energy, when it condenses into the lower temperature metal. But nonetheless, the Thomson energy is going to be something. They calculated all this for a 100 amp 10 volt arc, if I remember, and that means that 80% of your cooling, 80% of your 1 volt ends up to be about 4% of your total 1,000 watts that you have in your system. Now, what are these other two? The work function and the anode voltage drop. Well, the anode voltage drop we already talked about. The anode voltage drop is the fact that if my electron is sitting up here with 1 volt of equivalent Thomson thermal energy, it's in the middle of the plasma column. In order to get down into the metal, it has to punch through this voltage that is created by the cold gas in the boundary layer at the surface of the anode. And I have to apply enough voltage to the arc to accelerate that electron through this cold, very, very weakly ionized plasma layer. Now, that's the layer that the physicists can deal with, okay? They can't deal with up here, but they could deal with a very, very thin region, about 1/10 of a millimeter or 2/10 of a millimeter thick right against the surface. So it has to overcome the anode voltage drop, or the anode fall voltage, which is on the order of 4 or 5 volts. Let's call it 5 volts. If we call it 5 volts, it's going to be about 20% of the total energy. And then there's the work function. Anybody know what the work function is? The work function, again, we're talking about an electron's going from whatever the energy level is up here through the boundary layer and into the metal. Electrons like to be in metals. If they didn't like to be in metals, the metal would blow itself apart. It wouldn't be stable. It would become a gas. It wouldn't be a condensed phase. I mean, electrons want to stay in metals, otherwise they wouldn't stay in metals. And if they had a positive, if they had a negative Gibbs free energy to go out of the metal, then they would. Well, it turns out electrons, when the metals come together and there's metallic bonding, the electrons lower their energy level down to, anybody know what they lower their energy? The outer shell, the outermost electron in the metal lowers its energy to a certain level. Anybody know the name of that level? Named after a famous physicist who did the reactor pile experiment in Chicago, underneath the Chicago Stadium. Fermi. The Fermi level, right? So it turns out an electron, the highest energy of an electron in the metal is at the Fermi level by definition. That is, the Fermi level is the highest energy, is defined as the energy level at which the electron sits. So if this is the zero of energy, an electron just sitting here at absolute zero in free space, that's zero energy. There is an energy below that where the Fermi energy is, and then you have these electron bands. Remember these electron bands from semiconductor theory and things like that? These bands where electrons, quantum mechanics says electrons can reside below the Fermi energy, below the Fermi level. Well, the energy difference here is called phi, the work function. And the work function, if I go back to this guy, same phi, the work function is the amount of energy it takes to strip an electron out of the metal. If I'm at the cathode, I've got to take electrons out of the metal. And the work function is the amount of work that you have to do to get cathode emission, to strip electrons out of the metal. You have to raise them from the Fermi level up to the zero of energy to get them out of the metal. And so we have this plot, which is the energy level of electrons. Here's the Fermi energy, here's the work function. There's an anode voltage drop right at the surface. There's also the Thomson energy above this. When an electron goes from a high temperature up here in a plasma across an anode voltage drop and then decays down and is bound in the metal at the Fermi level, the total voltage drop is the thermal energy plus the anode voltage drop plus the work function as it decays to its ground state in the atom. And that is going to be 5 or 6 volts. And if you add all this up, you find that the electron flow carries about 50% of the current, 50% of the heat generated in the arc is carried by electron flow from the center of the plasma into the workpiece. If you go through, and Metcalf and Quigley go through and estimate the conductive heat flow through the gas across the thermal boundary layer, or actually the conductive heat flow across the thermal boundary layer, the conductive heat flow in a hot gas, the radiative heat loss, it actually is 2% in from the hot plasma and 1% out from the hot well pool. And then the evaporation from the well pool, you actually lose about 2%. And they're radiative they're radiative into the well pool is about 1%, radiative out of the well pool is about a 0.5% loss. So the net is only about a 0.5%. A lot of people think that, or in fact I see this in papers all the time, welding papers, people say, well, we lost heat by radiation from the arc. Yeah, you lose about 1% of your heat by radiation from the arc. You don't lose a lot of heat by radiation from the arc. And they say, well, but you can get a sunburn. Yeah, I got a sunburn once. I was once looking at I was at Alcoa Research Labs, and they were giving me a demonstration of welding very thick plates for liquid natural gas tanks. And I was standing from about here to where you are over there, looking at the arc through a shield. And the next day I was down at a welding conference in New Orleans, and I had this sunburn on my hand. I couldn't figure out what it was for a couple of days. It was just in this part of my hand. It wasn't up here. Well, it turns out when I had been holding that mask over I had shielded this part of my hand, and just watching that for about 60 seconds from that distance on a very reflective metal like aluminum had given me a sunburn. However, okay, that was 60 seconds. Typically, I'm fair-skinned. I might burn in an hour in a good sunny day, right? But a good sunny day is 0.03 watts per square centimeter. So what fraction of 10,000 watts per square centimeter coming from that arc did I have to get in order to sunburn myself in 60 seconds? Well, you can take 0.03 times 60 and come up with whatever you come up with, 2. And 2 over 10,000, well, that's not a very big percentage of total thermal radiation, right? So the radiation coming from an arc is a very small fraction of the heat loss from an arc. Partly because an arc is a spectral radiator, just radiates at specific wavelengths, very intense at those wavelengths, but just a few wavelengths. The well pool itself is only at 3,000 or around 2,500 degrees centigrade or Kelvin, either one. Who's going to quibble about 300 degrees at that temperature, right? You know you're hot. In any case, it's a Planck radiator, and actually, I don't know if I don't have that overhead with me, I don't think, but you have, it's the overhead that I use, 10 to the third watts per square centimeter. It turns out 2,000 Kelvin is only 100 watts per square centimeter if you had a black body radiation. So, for a Planck radiator. So it turns out the well pool doesn't it not being a perfect radiator, has a much lower emissivity and stuff, only loses a very small fraction of radiation too, so far as that goes. So in any case, 80 to 90% of the heat is carried by the electron flow. And that's why, if I were to go back and compare, I have a flame, an oxyacetylene flame that gives me 1,000 watts per square centimeter, but I can get 10 times that by going to an electric arc where the electrons punch through the boundary layer. When I said that an arc is an electrically augmented flame, I have a high temperature gas, just like I do in a flame, but in this case, the flame is limited, remember, by its heat transfer because you can't get heat conduction through the boundary layer very efficiently. But I have electrons that punch through that boundary layer. Those electrons have enough mobility, they effectively don't see the boundary layer. They actually do see the boundary layer in terms of the anode fall voltage. They have to be accelerated across it, but that actually carries some of the heat from the arc voltage in there with it. So that becomes important when we start trying to understand the physics of what happens when I use different shielding gases. And if I use different shielding gases, keep some of these guys out. We use different shielding gases for welding. A common one commonly used is argon. We use argon because there's 1% argon in the air. Argon is the most available of all the noble gases. It turns out that if the electrons carry 80% of the heat in an arc, that means that the gas boundary layer, the conduction and convection, is carrying about 20% of the heat. And if I just say I've got an arc and I'm running it with argon, it's an 80-20 split. Now, I told you, in fact, today, even today, if you go to the welding handbook that was just published 4 or 5 years ago or whatever, and you look on the under the physics of welding, it will tell you that it is the difference in ionization potential between helium and argon that causes helium to have better heat transfer, because that will give you a higher temperature plasma. Except I just explained to you, it's a metal vapor plasma, so it's irrelevant whether you're using argon or helium. If you actually take and you measure the temperature, spectrographically measure the temperature, okay, of an arc, and you do a helium arc on water-cooled copper, you can get temperatures of 18,000 degrees. If you do an argon arc, you'll get 12,000 degrees. And people say, aha, that difference in temperature of the flame is what gives you 50–60% greater melting in the in a welding arc with helium. Except that's not true. In fact, the certified welding engineering exam has that same question on it, and it basically asks the question, and the official answer, actually it asks the question in a way that asks you to use these differences in ionization energy to explain why helium's a hotter arc. It's wrong. If you actually measure a helium arc on a molten weld pool and an argon arc on a molten weld pool, because they both got the same metal vapor, the temperatures of the plasma are essentially the same. Remember what I said at the beginning, the high pressure arc is only going to go to a temperature sufficient to generate enough electrons. And if I got metal vapors there, the metal vapors are easily ionized and they'll produce enough electrons. And so the arc doesn't care whether it's argon or helium from an electrical point of view. The energy carried by the electrons, they could care less. Those argon and helium atoms are just, it's the tortoise and the hare type of thing, where these are the electrons of the fast-moving species. They don't even see these slow-moving ions. So it turns out, what is the explanation? Well, the explanation is simply that the heat carried by helium across the boundary layer is about 3 times as effective. And how can you say that? How can you prove that? Anybody know what the ratio of, or what the kinetic theory of gases says about heat transfer of gases in their molecular weights? Don't remember that? Neither do I, but anyway. It basically says the thermal conductivity of a gas is proportional to the square root of 1 over the molecular weight of the gas. Okay? Let me do molecular weight. Like, Okay? It turns out for argon, the molecular weight is 40. For helium, the molecular weight is 4. So the ratio of K of argon to K of helium is equal to, or is proportional to, the ratio of their molecular weights, which is, in this case, 4 over 40, because it's the inverse, right? And that's 1/10, and the square root of 1/10 is 1/3. Helium has 3 times the thermal conductivity of argon just because it's a lighter element. That means, and since it's the thermal conductivity that controls the heat transfer across the boundary layer, if I'm going to get 80% of my heat from the electrons between a helium and an argon arc, I'm going to get 20, and I get 20% by transfer, by conduction and convection across the gas boundary layer. With argon, I'll get 3 times as much. So the total here is 140% as opposed to 100%. I have a 40% increase in the heat transfer efficiency when I use helium as opposed to argon in welding. Has nothing to do with ionization potentials, in spite of the welding handbook and what it says. I actually once gave a talk about 10 or 15 years ago at a conference. It was a conference keynote talk, and my theme was what's wrong in the welding handbook. Okay? And there's dozens of things that people just haven't thought hard enough about the problems. In any case, so helium is more effective, and people in the United States will use helium when they need better heat transfer in a gas tungsten arc. Or they'll use argon, helium, oxygen mixtures when they're using what we call gas metal arc welding, where you use a wire electrode. Why did I say in the United States? Why doesn't the rest of the world use helium for welding? Anybody know? Yeah. Oh, no? Well, first of all, the helium in the air is not 1% like argon. It's like 0.003% or something. It's there in parts per million. There's not a lot of helium. And unfortunately, you can't synthesize helium by any practical economic means. You can have a fusion reactor and synthesize helium, but that's not exactly economical. So then the inert gases were basically given to us by nature. They were created when the supernova exploded and things, and somehow in the years of the universe we got a certain amount of helium and argon. We got a lot of argon, 1% in the air, a lot of air out there, but not as much helium in the air. It turns out the United States has about, well, in terms of non-air helium reserves, we basically have 100% of the world's helium reserves. And it happens to occur that in Oklahoma and Texas, in the natural gas, some of the natural gas deposits have 5% helium in them. Now, don't ask me why, I'm not a geologist, but that's just the way it is. So in the United States, a liter of liquid helium will cost you $2 or $3 for a liter. A liter is about a quart, right? In Europe, where they basically have to get their liter either by buying it from the United States or by liquefying air, and then liquefying a lot of air, it turns out liquid helium might cost you $10 or $15 a liter. And at those prices, it gets too pricey to do welding. But at $2 or $3 a liter, we can use helium in the United States, and we do. We blow it off, and we're increasing the concentration out there for everybody else that's going to distill the air. And one day, we won't have any left, because we're going to use up all our natural gas deposits in Oklahoma and Texas. By that time, I'll be retired, and the rest of you can worry about it, okay? But there is a problem here, and there have been a number of studies for many years, 30 or 40 years. The government had a guaranteed price for helium so that they would extract it from the natural got, because before that, people were just burning it in their gas furnaces in their basement. It was just going up the stack. In fact, they were getting less heating content when you bought your gas from the gas company because it had all these inerts in it, right? So the government, until about 10 years ago, had a guaranteed price floor for helium, And so we have reserves of helium. We have old salt mines in Louisiana just full of helium. So if you want to talk with a high squeaky voice, right? You've done that, right? In any case, so we use helium, the rest of the world doesn't for welding. Hydrogen. Well, hydrogen is a lighter gas. If I went through hydrogen rather than helium, this would become 2 for diatomic hydrogen. And so this would become 1 over 4.5 or something like that. And so a little bit of hydrogen in argon will significantly improve the thermal conductivity across that boundary layer. People did around the first half of the last century did weld with 100% argon. They actually took a little electric arc and they blew straight hydrogen at that, and they struck the arc and they got a very, very hot flame. You could get 5,000 watts per square centimeter with these flames. You actually weren't getting the electrical energy into the workpiece, so you didn't have the electrical flow. You just had a very hot flame between 2 electrodes. The only problem with that is if you didn't handle it quite right and you're igniting hydrogen and you're doing this in air, there were a few people who blew themselves up. So the atomic hydrogen torch, which is what it was called, which was just 2 electrodes that designed to shoot a hot flame at the weld pool, was used. Another problem is you can't use hydrogen on steels, on carbon steels, because you get hydrogen cracking. Who wants to weld in a 100% hydrogen atmosphere? Well, you can say who wants to weld steel in a 100% hydrogen atmosphere, but those cellulosic stick electrodes I talked about, have been passed them around. The cellulosic electrodes, what's cellulose? It's a hydrocarbon, right? Turns out that atmosphere that you generate by burning up the paper around that steel rod is about 60% hydrogen. So cellulosic electrodes are called high hydrogen electrodes. The 7018 electrode, which has the mineral coating, it's called a low hydrogen electrode, or commonly called low-high out there in the industry. Well, turns out that you can't weld carbon steels, get low hydrogen by using argon hydrogen mixtures, but stainless steels, which don't have these hydrogen problems, quite often people use an argon 10% hydrogen or argon 5% hydrogen. And the hydrogen gives much better thermal conductivity, even better than the helium, even with small concentrations, because of the lower molecular weight. But in addition, there's another thing. If I use CO2, well, this is pretty heavy. That's 12 plus 32. That's 44 as a molecular weight of CO2. But it turns out it gives you a higher heat transfer. In this case, because, saying actually with hydrogen as well, there's something called the reactive thermal conductivity. Up here in the plasma, the energy in the plasma is going to cause that diatomic or triatomic gas to dissociate. So I don't have hydrogen, I have atomic hydrogen, H. I don't have H2, I have 2H, right? 2 hydrogen atoms as opposed to a hydrogen molecule. Or I have carbon monoxide plus oxygen, plus a monatomic oxygen, when this dissociates into CO plus oxygen. When I do that, I have to put energy in that to break the bond. But when it hits the surface of the weld where everything's cooler, so up here, I put energy into breaking those bonds. Down here in the boundary layer where everything cools off, it recombines. The oxygen and the CO recombine to CO2. The 2 hydrogens combine to H2. And when it does that, it gives up what we call the heat of recombination. The heat that was absorbed in dissociation is readmitted down in the boundary layer as the heat of recombination. And that extra heat in the boundary layer ends up getting transferred, gives a hotter boundary layer, and gets transferred into the workpiece. In plasma physics, it's called the reactive thermal conductivity. And if you look at a plot, which I didn't bring the plot, but if you look at the plot of thermal conductivity as a function of temperature, there's a peak at around 3,000 Kelvin because above 3,000 Kelvin, the gas is absorbing heat by dissociating the atoms, the polyatomic atoms. Below 3,000, or at 3,000, they recombine, and below 3,000, they're just molecules, and so there's no reactive thermal conductivity. But this rejoining of the molecules in the boundary layer actually enhances the heat transfer with polyatomic shielding gases. So when you go out there in the real world, you'll find that welders use all kinds of different gases, and nobody virtually in the welding community has the foggiest idea of why one gas transfers heat differently than another. Although, frankly, the physicists and the chemists understand, but they would never talk to a welder, so what difference does it make? Right? Let's talk a little bit more about heat flow to the anode. Because I have this fact that the current flow, the electrons carry the heat, if I am using gas tungsten arc welding, which is officially called DC electrode negative, and so my electrode is, and this is a tungsten electrode because it's gas tungsten arc welding. My electrode is negative, my anode is down here, is the workpiece. This is also, in the jargon of the trade, called more commonly straight polarity. Now, if I go over here and look at the electrons coming out, I actually will find that the electrons coming out of the cathode will cool the tip of the cathode, because the electrons are essentially being vaporized from the surface. You can think of it, sometimes they call it in the literature, the heat of vaporization. You're extracting them, you have to put in the work function voltage to get them out of there. And so they actually, that work function voltage that you're extracting by taking the electrons from a low energy state and putting them in a high energy state is the same thing as evaporating electrons from the surface. They're carrying the heat of vaporization. As they go from the solid phase into the gaseous phase, they are evaporating into a gas phase, is one way to think about it. That means they actually cool the electrode. And in fact, Professor Savage at RPI once took an optical pyrometer and measured the temperature. He shielded off the arc, and he measured the temperature of the electrode, and the gas tungsten arc electrode was hotter a couple of millimeters from the tip, because it actually is being cooled by the surface, by the electrons coming out of the surface. By the same token, when the electrons go into the anode, they're heating the anode. They carry that work function voltage in there. And in fact, that means that the partitioning of heat is you get about 1/3 of your heat to the cathode and about 2/3 of your heat to the anode. In DC, in an arc, you do not have symmetric heating. The anode gets hotter more quickly than the cathode. It turns out that if you use a tungsten electrode and let's say you have a 1/8 inch or a 3 millimeter diameter tungsten electrode that you're going to use for welding. If I run that in DC electrode negative or straight polarity, that will probably run between 100 and 125 amps before you would melt the tungsten tip. If you carry too much current through a 3 millimeter electrode, it's going to melt. Okay? If I was running that with DC electrode positive, or what we call reverse polarity, it will only carry about 60 amps before I melt the tip. And the reason is the anode heats more effectively than the cathode. There's actually electron cooling at the cathode, a certain amount of electron cooling. So the tip is cooled by electron evaporation. The anode's heating is heated by electron condensation. That's the work. These are both the work function voltage, but it's not symmetric because electrons are flowing different ways.
Can you explain how the welding process actually is in those two? They're different.
What, in this one and this one?
How you physically weld.
Oh. Well, I was going to get that. Let me explain this one first. Okay. So this is gas tungsten arc. There is no there is no melting of the electrode. It's sometimes called a non-consumable electrode process. Originally, people tried to use carbon electrodes, but carbon electrodes, if you accidentally hit the liquid pool, it dissolves in the molten steel, and that's not good. So anyway, they found in 1932 there's a U.S. patent by a guy that basically is the gas tungsten arc welding process, where this guy was welding magnesium using a tungsten non-consumable electrode. So you're just melting the pool. Now down here with gas metal arc welding, which was invented about the mid-1950s by a guy named Al Lesnowich, who is still alive, but had been president of the American Welding Society for a while. Al Lesnowich tried, actually there were other people in the 40s in addition to Al, who had tried to use just a bare steel wire with an argon shielding, or what they found was argon with a few percent oxygen, or argon with a little bit of CO2, gave a stable arc. And you actually feed the wire in. You've got rollers and you're pushing the wire in towards the arc, but because you now want to melt this off, and so you make this one the anode. There's other reasons why you make it the anode. It's more stable, for one. But this becomes the anode, and you want to melt the wire off and essentially fill up a groove here. So here, typically, you'll just have two square end pieces of metal. You're just trying to melt them together in gas tungsten arc. And there's not necessarily filler metal unless you want to add it by a separate wire on the side. And it just kind of gets melted into the pool with everything else. There's no current. Well, there can be current going through that wire, which is called hot wire, GTAW, as opposed to cold wire feed. But this one, you actually are running your welding current. Your arc current goes through this electrode. Actually, it goes through the electrode. Actually, the current does go that way because the current goes the other way, because Ben Franklin thought the electrical charges were positive rather than negative, but we won't get into that. Did you know that? Current goes opposite of the electrons, right? Because Ben Franklin made a mistake. Anyway, what we have here is the electrode is iron, aluminum, and nickel, and I actually will melt off drops. And those drops come shooting off there at about 100 times a second in the most common type of welding process. And I basically have these little drops that fill up the pool. Same time, and when I do my stick electrode welding, those consumable electrodes with stick with flux, I have a similar type of thing where I'm running the current through here, and most commonly I will have the workpiece is the anode, because I'm trying to melt that electrode. Is that what you wanted in terms of explanation? So, are we running out of time here? In another 2 minutes. There is definitely a difference in electrode heating. Because of that, well, there's actually lots of things that come out of that in terms of arc physics and how we actually weld. In gas tungsten arc welding, I like to run with this polarity, but there's a problem when welding aluminum, which is one of the most, actually, the first big application of gas tungsten arc welding in industry at all was in World War II for putting aircraft together, aluminum structures of aircraft. In fact, gas tungsten arc is still widely used, more widely used for welding of aluminum than is gas metal arc or some other things compared to steel. Gas tungsten arc basically can weld virtually anything. They use it to weld iridium, which melts at 3,000 Kelvin. Do you have a question? Yeah, this is called TIG in Europe, and this is MIG in Europe. These are the proper names. The reason are by the American Welding Society, and that's because there's a guy who died a few years ago in his 90s named Halleck Campbell, who graduated from Harvard. Did I tell you a story about Halleck? Halleck, having been a Harvard grad, but a welder also, was a stickler for different terminology. And so the welding, there's a set of terms and definitions in welding that were basically written by this Harvard guy. And Halleck was kind of a character. He once, back in the mid-80s, I was working with the Navy in Japan, and Halleck took exception. I had written a paper called a parameter, and I used the word parameters in the title of the paper. And we were doing a parametric study or something. And he wrote to me in Tokyo, and he says, "You used the word parameter incorrectly, blah, 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 blah," okay? And I went to the unabridged dictionary, and there was, like, definition number 2 was my definition of parameter. And it turns out, dictionaries will give you someone actually using the word in a sentence. And it turns out the sentence came from P.W. Bridgman. Well, you have to know that P.W. Bridgman was Percy Bridgman, who was a professor at Harvard in the 1930s when Halleck graduated, right? So I Xerox this thing, whip a nice friendly letter back to Halleck saying, "Halleck, I was using definition number 2," and I get this hand-scratched note back from Halleck says, "Bridgman, how could you?" He didn't like the way Bridgman had used it, but I mean, anyway. So, but Halleck was a stickler for terminology. TIG stands for tungsten inert gas. MIG stands for metal inert gas. You're using a metal wire. But the problem is, as Halleck pointed out, we don't use inert gases. We don't use 100% argon. In fact, if you use 100% argon, you get an unstable arc. You have to add typically 2% oxygen or 5% CO2. Or sometimes you weld here with 100% CO2. And so Halleck would not accept MIG as a terminology. So he made sure that Americans, the Welding Society officially calls it GTAW, GMAW. Everybody else in the world, including the welders in the United States, call it TIG and MIG. Okay? Now, in Japan, where they are very respectful and listen to Halleck, they basically call it MIG and MAG. And MIG means when you're using mostly inert gases, and MAG means metal active gas. So if you're using 100% CO2, the Japanese will call that mag welding for metal active gas, because the CO2 does react with the weld metal. And in fact, I think I mentioned we're dealing with a problem in some welds in a building here in Boston right now that don't have the properties people want. And part of it is there's the welding electrode has a certain amount of manganese and silicon. And you can weld this particular electrode, the manufacturer says, you can weld it with 100% CO2, gas metal arc, and you'll get this set of properties. You can also weld it, they say, with 75% argon, 25% CO2. So only 25% CO2. And you will get this set of properties, which are higher strength because you end up with more manganese and silicon. With less reactive gas, you leave a higher concentration of manganese and silicon and you get a more highly alloyed weld deposit, and you get about a 10% boost in strength and potentially cracking. Anyway, they don't tell you that, but you got to be careful that you don't get cracking, which is actually what happened, but nonetheless. So there are lots of complications, and my best advice is if you have a problem, call a welding engineer who knows something, and if you can find one, give me their address.